your screen.
Yep, says recording started.
Okay, so hello everybody. Welcome back to another episode of the podcast. In this episode, I'm joined by Woody Leonard, who works on the quantum computing team at Microsoft. So hello, Woody.
Hey, how you doing? I go by
I'm
my last name, Woody. Full name's Leonard Woody. Work with the Azure Quantum team on our quantum scale messaging, and specifically, I work with customer engagement. So we have an internal team of Azure Quantum Field Ambassadors that I helped lead, and the Azure Quantum MVPs. So that's what I'm currently doing.
Sounds good. Now, I'm really excited about this episode because we'll get to know all about quantum computing. So we'll get right into it. I guess you can just start off with explaining the groundwork. So just laying the foundation. So what exactly is a quantum computer and what makes it different from like a traditional computer?
Yeah, so my elevator pitch, I guess you might say, for quantum computing is it's trying to do computation at the level of an electron. And, when we start to observe things at that kind of subatomic level, things get very weird that we don't see at a macroscopic level. Things like quantum tunneling, entanglement, words like superposition, they just don't manifest themselves at our macroscopic level. So basically, we're trying to exploit those weird phenomena to do computation that we just can't do on classical systems. So to qualify what a quantum computer is, there's different hardware architectures that we can use. We can get into it in the interview, but some people will use ion traps. Others will use what are called superconducting qubits. You can use photons. But basically, you need a two-level system, quantum mechanical system, that can represent a zero state and a one state.
I see. Yeah. So I guess before I get to my next question, can you just quickly explain like the three concepts you mentioned? So superposition, entanglement, for people who are not familiar with those.
Yeah, sure. So superposition is a way that a qubit can be in what we call a linear combination between a zero and a one state. So that's unusual in our classical world. When we have a digital bit, it's either a zero or one. Superposition is a quantum mechanical effect where it can be in a combination of states. And when we go to measure that qubit, there's a probability that it'll be a zero or a one. And depending on what state the qubit is in, determines the probability of what that's going to be. So it could be 50-50, like a coin flip, or it could be 75%. We know that it'll come out of one, 25% it'll come out of zero. But in the superposition of a zero and one state, we don't know for sure which one it's going to be. Entanglement is another quantum mechanical property where two qubits can basically interact with each other and their measurements become correlated. So that when in certain states, I can measure one on one qubit, and when I go to measure the other one, I automatically know that that's going to be a one because they're entangled. And that again is unusual at the classical system. When I go to measure a bit, I don't automatically know what the other bit is going to be just for measuring one bit, and so that's entanglement.
That's good. Yeah. So I guess what are some of the key applications of quantum computers? Like what? So say we have this new level of computing power. What are some of the real world problems that it can solve?
Yeah, there's quite a few out there. We at Microsoft have come out with what's called an Azure Quantum Resource Estimator, and I think the nice thing about that is we can take all the different proposed applications of quantum computing, like finance and transportation and logistics and optimization, chemistry, and put them into the resource estimator and see how many qubits is actually going to take to apply a quantum computer to this type of problem. And when we put in different use cases, we see the most near term to be chemistry and materials science, which kind of makes sense if you think about it, because those two types of sciences and industry deal with quantum mechanics at the very low level. And so you would suspect that a quantum computer that can emulate those types of properties and actually be in those particular states that you're looking at would be best applied to chemistry and materials science. So there's a wide swath of potential applications. We feel like the closest is chemistry and materials science.
I see. And is the current research, so like for example, the current work Microsoft is doing, or like any other computer or any other companies, into quantum computers, what's the main goal? Is it like to make it accessible to everyone? So like one day, like 100 years in the future, like we would all have access to that? Or is it more like a solution that like a company is solving? Like, okay, we have this capability that others don't, so use us to develop your applications.
Yeah, I think it's a plethora of different applications and goals that different companies have. I mean, you have governments that are involved, and they have their own reasons for getting involved in quantum computing. As a for-profit company, ultimately we're going to want to make profit from quantum computing. But part of that is empowering, innovators across the world to be able to access quantum computers. And so we've done that through Azure Quantum. We have a number of different hardware architectures that you can use on Azure Quantum. I think the holy grail is what we call fault-tolerant quantum computing. And so when we get to that point, we can come up with a quantum computer that has enough qubits and there's not so much noise that we can actually do a lot of these applications that we've talked about just now, especially around chemistry and material science.
Yeah. So when building a quantum computer, like what are the main challenges? Because I'm sure so there's detailed physics that people know about this, but we're like actually building that hardware. What
Yeah.
are like the challenges with that?
Well, it's funny because we talk about fault tolerance, right? And I mean, I've studied fault tolerant systems from a classical standpoint, but it becomes very important in quantum computing because the qubits are very noisy. So when you go to measure a qubit, there can be a lot of noise based on that measurement. So, 99% of the time it's right, but 1% of the time it's not correct when you go to measure it. And that may not sound like a big deal, but when you do those measurements millions and millions of times in a computation, it becomes a very big deal. They're also not stable very long, usually. A lot of the hardware architectures are not stable, so you have to do your computation very fast. And there's a quantum mechanical phenomenon called decoherence. So the states of the qubit actually decohere over time, and it gets to a point that the state is so decoherent that it is no longer useful to you anymore. And so the noise of the system and trying to isolate qubits from their environment is one of the huge challenges that we have within quantum computing.
I see. Yeah. And I guess so building on top of this, so as research continues into quantum computing, as like more hardware capabilities are brought up, as well as like new physics related breakthroughs, what's the like future of quantum computers, say like in the next 5 to 10 years? Like what are some of the key advancements targeted for that time period?
Some of the key applications,
key advancements. Yeah, application advancements. Like what?
Yeah, I think the first advancement to kind of keep your eye on is what we're calling kind of practical quantum advantage. So, back in 2019, Google showed how a quantum computer could do something faster than a classical computer could, but it wasn't a commercial.
The quantum supremacy, I think.
Yes.
It was.
Yes.
They
So a
targeted
lot of people
that.
refer to it as quantum supremacy.
Yeah.
So they achieved that in 2019, basically, but it wasn't a problem that is commercially valuable or really helps society in any ways. In a lot of ways, it was like, beating a computer in chess or tic-tac-toe or something like that. It just isn't useful, but it did it faster than a classical computer can do it. Practical quantum advantage is actually finding a commercial application of a quantum computer for a problem that's commercially valuable. That can be done faster than a quantum computer, or faster than a classical computer, I'm sorry. And so that would be the next milestone for quantum computing, I think, is that we're able to achieve practical quantum advantage. So, it may be chemistry, it may be material science, could be finance, but some commercially valuable problem that a quantum computer can do faster than a classical computer.
And what resources would you recommend for people who want to get into this field? Not like technically, not as to work, but just to learn more about quantum computers. One of them you mentioned was like Microsoft's own Azure Quantum.
Yeah, we have Azure Quantum. I'd be remiss if I didn't mention my book, Essential Mathematics for Quantum Computing, that I just published about a year ago.
Can we find it on Amazon? I'll link it in the description below.
Oh yeah. I'll definitely give you a link
Sure.
to be able to do
So I'll have
that.
all the links down in the description below so you guys can check it out.
Yeah, definitely. I mean, if you're getting started, I think there's kind of two paths. If you just want a business overview of kind of where Azure Quantum is or quantum computing in general, I think that there's good resources through MIT. They kind of have a business overview type of class or deck that you can go through. Um, uh, to be truthful, there's some good resources from IBM out there. We have Microsoft Quantum Learning as well, journeys that I think are very good. So if you're just going for a business, kind of overview, there's also kind of, I think it's quantum computing for the beginners. I think it's called. We can get a link for that. So that's kind of a business overview. If you want to get more into kind of the technical ways that quantum computer works, a lot of it starts with mathematics, specifically linear algebra. So some people are familiar with linear algebra from undergrad universities. Some have never come across it, and that's why I wrote my book, is to kind of get people up to speed on the math that you need. And then another good resource is quantum katas that we have at Microsoft. I can get you the link for that as well. And we use our own language called Q#, which is a quantum programming language. And it gives you basically puzzles and problems to solve that you would encounter in quantum computing very often.
And what about someone who wants to pursue a career in this field? Like, what are like the necessary background? What foundations do you need to cover for that?
Yeah, so I think if you're, say, an undergrad or something like that, majoring in computer science and then taking physics as well would be a good combination. If you could do a double major in physics and computer science, like I did undergrad, I think that's going to prepare you well. If you're kind of in the work industry now, there's a lot of different ways that you can apply yourself to quantum computing. Probably the biggest division is software and hardware. So I would just try to get into it. There's 3 programming languages out there: Qiskit, Circ, and Q#. We support them all on Azure Quantum. And I would just start, getting on there and just playing around with them. And then you could start studying some of the hardware that we offer too, like ion traps, superconducting qubits. We have topological qubits that we're pursuing at Microsoft. And so, the hardware is going to get really into physics. So if you decide that you want to go down the hardware path, then you're really going to have to start to get into physics and stuff like that. If you decide you want to do the software route, then you'll need to learn those languages. 2 of them are based on Python, so that'll be something that you would need to learn if you don't know it already. And then you need to kind of start studying quantum algorithms. So some of the beginner algorithms are like Grover's search, Shor's algorithm, and be able to kind of program those together. And that will get you started on kind of one of those 2 paths if you want to get into quantum computing.
I see. Yeah. One thing I wanted to touch on, you mentioned before that governments are also involved in like this quantum area. So I wanted to know, is there any type of like policies that they create specifically for like quantum research, or like to restrict its development or something like that? Is there any type of like policy involvement there?
It's not so much restriction. I think right now, the National Quantum Initiative Act is something the U.S. federal government passed in 2019, and it gives a lot of funding to different U.S. government agencies like NIST, the Department of Energy, different agencies throughout the U.S. federal government. And the biggest thing is people are trying how to figure out how to build a fault-tolerant quantum computer. So within the United States, there's a lot of that. The EU, the European Union, is putting a lot of funding into quantum computing. I think the biggest thing is, we spend, I believe, around $1 billion a year on quantum computing in the U.S., and I think China is around 15 billion a year.
Is
And
that
if you,
government spending or
yeah,
like private
government spending, and so that's a 15-to-1 type of ratio. So, as an advocate of quantum computing, I hope the U.S. government and really all governments around the world will spend more on quantum computing because I do think it's going to be a differentiator in the future.
I see. Yeah, and I guess we'll just end off with this question: what is the most exciting part about like the potential of quantum computing for you personally? Like, what do you think? Okay, like once we get to this point, like that's like really the good, like juicy stuff. with when it comes to quantum computing? And what's the most exciting part for you there?
I mean, to see a quantum computer actually implement Shor's algorithm, be able to factor really large numbers and break RSA. I don't know if that'll happen in my lifetime, but that would be pretty exciting. So
Sounds good. Yeah.
I mean,
Well, thank.
yeah.
I was going to say, well, thank you so much, Woody. This has been really insightful. I've had a personal interest in quantum computers for a really long time, and I hope you guys have enjoyed as well. Found this chat a bit valuable, gotten some value out of it. I'll put all the links down in the description below so you guys can find them. So all the resources will be there. And thank you again, Woody, for your time and answering all my questions.
Sure. Thanks for having me on.
Yeah. Thank you so much.